Hi, hello, namaste. We will solve for 1D potential barrier, or we can also refer to it as quantum tunneling. We have solved for something like this in our previous videos where we only had to deal with one potential barrier and we referred to this as V naught. Now, since it can be expanded, and when I say expanded or stretched, it means that it's like a wall, right? If we, let's say, stretch this from here, right? So it can become something like this. It becomes a thick wall. You can imagine it in that sense. And it has some widthness, like let's say 0 to a. So how will the particle, right? How will the particle behave when we have something like this? So this is what we are going to understand together in this video. So you might see a lot of stuff in this particular diagram, as you see, but I will simplify it to you in the very easiest way possible. So what we observe is that when we shoot a particle in this, so in region 1, when we shoot a particle, we observe oscillation and the particle gets reflected back, right? But as it penetrates inside this region of region 2, which we refer, so in region 2 the particle penetrates, right, and it decays and the particle reaches partially 0. That means not exactly 0 but partially 0, and then it again gets further in region 3, and since there is no incoming wave from the positive infinity, we only observe a moving forward wave. Also, the energy is less than V naught. What this means is that the potential barrier has high value compared to the particle's energy. One important thing before we begin: during this entire derivation, energy never splits. What splits is probability. So every probability, so every particle always has the same energy. Either it tunnels through completely, or let's say it gets reflected completely. So with that, we can just start with the derivation. So we start with time independent Schrödinger's equation, which is basically given by minus h cut square by 2m d square psi by dx square plus v of x of psi is equals to e of psi. And now we rearrange this equation. We are rearranging it. So d square psi by dx square plus 2me minus v naught by h cut square psi is equals to 0. Let's just consider this as v and not v naught. I'm sorry. Okay, now let us form our potentials, which is given by v of x for each region, right? So 0 for x less than 0 in region 1, v naught for 0 less than equals to x less than equals to a in region 2 or R2, and 0 again for x greater than a in R3. We are going to work with region 1, region 2 and region 3. So for region 1, where our x is less than 0 and our potential v naught here is 0, so v naught, not v naught, sorry, our potential v is going to be 0. So again our Schrödinger's equation gives or becomes something like this, where d square psi by dx square plus 2me by h cut square psi is equals to 0, where my k square, we are going to refer to it as this value which you see here, which is 2me by h cut square, which we can write as k is equals to root 2me by h cut square. And therefore our equation becomes d square psi by dx square plus k square psi is equal to 0. And from this equation, we can construct our general solution, which is a e raised to ikx plus p e raised to minus ikx, where this is my incoming wave and this is my reflected wave. We move to our region 2, R2, which is given by this, which is 0 is less than equals to x is less than equals to a, and my v becomes v naught here because of the potential region. And of course we are again going to use Schrödinger's equation, d square psi by dx square plus 2m e minus v naught upon h cut square psi is equals to 0, because we have the value of v here, right, and which is v naught. And again we are going to refer to this overall region 2 in the form of kappa. So this whole equation will be referred to as kappa, indicating that this is a region of decay where our particle partially becomes 0 and not completely 0. So we put this as 2m e minus v naught by h cut square. But if you note carefully, see, our e is less than v naught, right? So we need to put v naught, as v naught is bigger than e, so we need to reconstruct it in this way, as our kappa become, also this is root, so our kappa becomes 2m v naught minus e by h cut square, right? So we are going to just put it inside this. So d square psi by dx square plus kappa square psi is equals to 0. Voila. And our general solution according to this is c e raised to kappa x plus d e raised to minus kappa x, which is going to be our psi 2 of x. And by the way, this is going to be a psi 1 of x. And similarly, we are going to construct for region 3. So for region 3, where my x is greater than a, right, and my v is again 0. So same equation as R1, by the way, which is d square psi by dx square plus 2me by h cut square psi is equals to 0. And my again of course d square psi by dx square plus k square psi is equals to 0. And my general solution here is psi 3 of x, which is f e raised to I k a. And so there is no reflected wave here because nothing is coming from positive infinity, as already mentioned. We are going to look into the boundary conditions for all of these three regions. Boundary condition. So the wave function and its first derivation must be continuous. So we construct for continuity of psi. Therefore, continuity of psi at x is equals to 0. Psi 1 of 0 is equals to psi 2 of 0, right? Which is, and also we need to take the derivation of this equation. So we are already mentioning it here that d psi 1 by dx at 0 and d psi 2 upon dx at 0. Substituting this will give us for this one, firstly a plus b is equals to c plus d. I'm going to call this as equation 1. And for this one, which is ik a minus b is equals to kappa c minus d, and I'm going to call this as equation 2. Now we need to construct continuity equation of psi again, but for x is equals to a. So therefore continuity of psi at x is equals to a. So psi 2 of a is equals to psi 3 of a, and similarly what we did here is psi 2 d psi 2 upon dx at a and d psi 3 upon dx at a. Since we are adding at x is equals to a, so our equation will be in that sense that c, substituting c e raised to kappa a plus d e raised to minus kappa a is equals to f e raised to I k a. We are going to call this as equation 3. Now again, this was for this part. Now for this part, it is going to be, obviously we take kappa already out, so c e raised to kappa a plus a minus d e raised to minus kappa a is equals to I k f e raised to I k a, and we are going to call this as equation 4. And let me be clear that our goal is to find f upon a, because the final formulas is, because t is f upon a mod square, right? So we are going to find f upon a. That is our aim, right? So we are going to simplify this as much as we can. So we solve equation 3 and 4, right, for c and d, because in equation 3 and 4 we have c and d in it, and we are going to just simplify it as much as we can. So we define one thing is that, let's say we take x is equals to c e raised to kappa a and our y as d e raised to minus kappa a. So equation 3 and 4 becomes, equation 3 and 4 becomes x plus y is equals to f e raised to I k a, and I'm going to call this as 3 dash, and the next one, which is fourth equation, kappa, which was outside, so k x minus y is equals to I k f e raised to I k a, which I'm going to call this as 4 dash. So now what we are going to do is, the next step seems to be very simple. So we do add and subtraction, and add and subtraction of what? So addition of 3 dash, and so first we do the addition of 3 dash and 4 dash divided by kappa. So if we do this, we add this and we divide this by kappa, which is 4 dash. So we have 2x is equals to f e raised to I k a 1 plus I k divided by kappa, because we have taken common for this value, and then we can just divide 2 on the other side. So x is equals to f e raised to I k a by 2 1 plus I k by kappa. And now once addition is done, we are going to move to the subtraction part, which is subtraction of 3 dash and 4 dash again, but divided by kappa. So if we subtract this, then of course we are going to get y values in this one. So our y values is 2y is equals to f e raised to I k a 1 minus I k by kappa, and again we are going to just put 2 on the other side, so y is equals to f e raised to I k a by 2 1 minus I k by kappa. We know what we did in this particular part, right, where we took x is equals to c e raised to kappa a. How about we take this part, divide it on this side and take the inverse. C is equals to x e raised to minus kappa a. And similarly, if we do it for this one, so I'll write it directly that my d is going to be y e raised to positive kappa a, right? So we can put the values of x and y in, because we have just got those two values. So first let's just put this one. So if I put it, it becomes f e raised to I k a divided by 2 e raised to minus kappa a, right? 1 plus I k by kappa. And for d is again something similar, which is f e raised to I k a by 2 e raised to kappa a 1 minus I k by kappa. Now we take a step back. We remember what we did for the boundary conditions, right? For boundary conditions, we took the continuity of psi at x is equals to 0, and we had this value, which is a plus b is equals to c plus d, right? So we are just going to put everything in this value. So what we have got c and d, right? We are going to put it back in this equation. So we are substituting c and d in this boundary condition, which, if you remember, we called it as equation 1. So if we put in equation 1, so my a plus b is going to be f e raised to I k a by 2 box bracket e raised to minus kappa a 1 plus I k upon kappa plus e raised to kappa a 1 minus I k upon kappa, closed. Similarly, in equation 2, which looked something like I k a minus b is equals to kappa c minus t, we can construct this in the same sense, which is going to be, because we have this, right? So I'll just take this side. Kappa f e raised to I k a by 2 box bracket e raised to minus kappa a 1 plus I k by kappa minus e raised to kappa a and 1 minus I k upon kappa. So now you see that we need to isolate a. So if we isolate a, we have two equations, that is a plus b is equals to x and a minus b, which is equals to y. So if we add this both equations, we have a is equals to 1 upon 2 x plus y. And what do we get out of this? So let's just consider this as equation a and this as equation b, okay? So from a, my x is equals to a plus b, right? And we already have a plus b in from the last equation, if you see, which is going to be my x is equals to f e raised to I k a upon 2 e raised to minus kappa a 1 plus I k upon kappa plus e raised to kappa a 1 minus I k upon kappa. And similarly, we can construct our y Now for this equation, we need to divide this equation by I by k, which makes it simpler. So I minus b first, if we divide it, it becomes f e raised to I k a kappa by I k e raised to minus kappa a 1 plus I k by kappa minus kappa by I k e raised to kappa a 1 minus I k by kappa. So now we can just say that my y is going to be f e raised to I k a by 2 e raised to minus kappa plus I k upon I k minus e raised to kappa minus I k upon I k. Now we add x plus y. And we already know that the addition of this gave us this, which is a is equals to 1 upon 2 x plus y. So we add finally that our x plus y, and we factor out the common terms. So a is equals to f e raised to I k a divided by 4, and e raised to minus kappa a, 1 plus I k upon kappa plus kappa plus I k upon I k. That was a big one. Now this is a big equation, definitely. Plus e raised to kappa a 1 minus I k upon kappa minus kappa minus I k upon I k. And we close the bracket. Now we need to just simplify this a bit. We can do it easily, and if we do it, I'll just show it to you. 1 plus I k upon kappa plus k plus I k upon I k. If we simplify this, it becomes kappa plus I k the whole square divided by I k kappa, and for this it becomes in minus, so it is minus of kappa minus I k upon I k kappa, and of course this is square, the numerator. So we just put whatever we just now did in this. So a is equals to f e raised to I k a by 4 e raised to minus kappa a k plus I kappa plus I k whole square upon I k kappa minus e raised to kappa a kappa minus I k the whole square upon I k kappa So we again common out things. A is equals to f e raised to I k a upon 4 I k kappa, and inside kappa plus I k whole square e raised to minus kappa a minus kappa minus I k the whole square e raised to kappa a. Now you can see something is happening here. We are getting closer to f upon a, so it's right there. So we will just do it, that f upon a is equals to 4I k kappa e raised to minus I ka the whole divided by kappa plus I k square e raised to kappa a minus kappa minus I k the whole square e raised to minus kappa a. My t is, of course, in the initial I told you that f upon a mod square. So if we just square this whole thing, we get into a more complex algebra. So let me just square the numerator for you. It's easier to square. So if you just square numerator, which is 4i k kappa square, and this is e raised to minus I kappa a square. Okay, and the denominator itself is a big thing. So kappa plus I k square e raised to kappa a minus kappa minus I k square e raised to minus kappa a, and we square it. So let's just simplify the numerator. So this is going to be 1, okay, and this is going to be 16. I'll write it 16 k square kappa square. Our numerator is definitely solved, but our denominator is still yet to be solved. So we will take it in a separate way. Let's just erase this first and solve denominator, because the answer which I wrote for the numerator is correct, but for denominator there is more to write. So by denominator we know is kappa plus I k the whole square e raised to kappa a minus kappa minus I k the whole square e raised to minus kappa a the whole square. So this looks like an equation which we can use, is that x minus y the whole square is x minus y and x complement minus y complement. So we solve accordingly that if we take a complement here for kappa plus I k, it becomes kappa minus I k, and for kappa minus I k, its complement is kappa plus I k. If we expand this, so expansions like we can, if we do it, then e raised to plus minus kappa a's complement is e raised to plus minus kappa a simply. So if we expand this denominator, as you see, we can write something like kappa plus I k the whole square e raised to kappa a minus, मैं दिख रहा हूँ क्या? बिल्कुल दिख रहा हूँ, कुछ नहीं दिख रहा है, माइनस kappa minus I k square e raised to minus k a, sorry, kappa a, and we bracket close here, and then we multiply it with its conjugate or its complement, and we multiplied this with its complement kappa minus I k the whole square e raised to kappa a minus kappa plus I k the whole square e raised to minus kappa a, bracket close. So if we expand this more, we have kappa square plus k square e raised to 2ka plus e raised to minus 2ka minus 2 kappa square plus kappa square minus k square the whole square. If you look carefully, this looks like a hyperbolic function which has a value. We can write it in the form e raised to 2x plus e raised to minus 2x is 2 cos h 2x. So if it is e raised to 2 kappa a and e raised to minus 2 kappa a, then we can simply write this as e raised to 2 kappa a plus e raised to minus 2 kappa a is 2 cos h 2 kappa a. Now we can factor this. First we will just put it inside the equation, that 2 kappa square plus k square the whole square cos h 2 kappa a minus k square, it's 2k square, sorry, 2k square minus kappa square the whole square. Now if you just factor out 2, then we can just take 2 out, 2 as common, so it is again kappa square plus k square the whole square cos h 2k kappa a, sorry, minus kappa square plus kappa square minus k square the whole square. And again we can just simplify this a bit more by stating that cos h of x is 1 plus 2 sine h square x. So this is an hyperbolic identity. So according to this we can put it in the equation that it is 2 into kappa square plus k square the whole square 1 plus 2 sine h square x. Oh sorry, at the place of x we have kappa a, right? Kappa a minus kappa square minus k square the whole square. Okay, so we can just write this as if you multiply this, so this is going to be kappa square plus k square the whole square minus kappa square minus k square the whole square plus 4 kappa square plus k square the whole k square sine h square ka. And now this can be written as, if you solve it, then this can be written as 4k square kappa square. So and then once we solve it, it becomes, we multiply 2 inside, so it becomes 8k square kappa square plus 4k square plus kappa square the whole square sine h square kappa a. If we substitute this into t, now we have our denominator. Now we are going to substitute this into t. It took so long. And if we substitute this into t, my t is going to be 16k square kappa square. We already got this before. And just insert this. It is 8k square kappa square plus 4k square plus kappa square the whole square sine h square kappa a. We can simplify this more by dividing this overall with 8k square kappa square, and if we do it, it becomes this equation, which is t is equals to 2 and 1 plus, because it is divided by okay, I'll write it that it is divided by 8 kappa square k square. So if it is divided by this, it becomes 1, and then this becomes kappa square plus k square upon 2 k square kappa square sine, as it is sine h square kappa a. And finally, if we take this, multiply this here, then if we just take this here. It is T is equals to 1 upon 1 plus kappa square plus k square upon 4 k square kappa square sine h square kappa a. Now if you remember, at the very beginning we did something like we took kappa as equals to actually kappa square as equals to 2m v naught minus e by h cut square, and our k was 2m e upon h cut square k square. Sorry, our k square was this. So now if we insert these two values at these places, we will have our final equation as T is equals to 1 upon 1 plus v naught square upon 4e v naught minus e sine h cut square kappa a. And this is our final equation. So the equation tells us that barrier width plays a dominant role because T depends exponentially on product kappa A. Even a small increase in the width of the barrier causes the tunneling probability to drop very rapidly. This explains why tunneling is significant only at atomic and subatomic length scale. A higher barrier makes tunneling less likely, yet it never switches it off entirely. So the equation reveals how particles properties matter. As particle of some energy E increases and approaches the barrier height, the tunneling probability rises sharply.